All right, so today what I'm going to do is go through the lectures at pretty high level that are on this test, which is when?
Next Wednesday.
Next Wednesday. I have the, I'm going to post the homework. I've been trying to decide what I want to do. So I decided that the first part of the homework is questions that relate to a lot of this, and the answers will not be provided. There's 3 questions, I think, at the end that are also part of this, but they're quantitative. And I thought, well, you know, I could make them gut it out. But I'll go ahead and give you the answers, the written of all the calculations, so you guys can get some experience doing the calculations. I thought that was more important than getting stuck, because there's so many units things that can pop up and make you get crazy answers if you don't take care of the units. So I'll go ahead and give you those answers with the understanding that you guys will be able to work it through. So you'll still have to hand in the homework. It's going to be due on Monday, by the way. Okay, but I'm going to assume that you won't just look at it and say, yeah, I know that. So you have to be able to write it down and work through it and make sure you have some experience punching the right keys in the calculator and all that good stuff, okay? And then I have 2 old tests, which I'm also going to put up on the website today, and then we should be good to go. Any questions on all that so far? All right. So yeah, getting back to the lecture. So again, this is just going through the subject matter at a kind of a high level. Make sure you guys understand these different points that are significant as far as the lectures are concerned. So we think about polymers in a number of different ways in terms of the control factors, and intermolecular interactions is one of those, and that's kind of captured here in this table. First off, we have covalent bonds, high energy, specific bond lengths, shown here in nanometers, which you multiply by 10 to get angstroms, and you have an idea of what those lengths are. And then we look at van der Waals bonds, dipole-dipole, and hydrogen bonds. And so you can see how these are, 2 or 3 times that of these covalent bonds. And of course, the covalent bonds are much stronger bonds, higher energy. These are relatively weak bonds and have longer distances, but not a lot longer. Okay, so these are all really short-range bonds. These guys, the covalent ones, they're, unless I tell you otherwise, they are eternal, okay? And then these other guys down here toward the bottom, they change all the time. They break and reform, okay? So don't tell me that they just break. They don't just break. They reform instantly. All right, so they are pliable bonds, but they're always there, and they always reform. As soon as the chains slide past each other, they reestablish bonds with other different moieties, groups on the polymer chain. Okay, that's something that I've seen a lot of issues with. And then molecular weight that we talked about in terms of how it controls things, and there's a certain chain length that's required to be useful to us, and there's a lot of chain lengths that are not as long as that, that are also going to give us useful products, just not plastics necessarily. And then, of course, crystallinity should be something that everyone's excessively familiar with at this point, and you should have a good understanding of how that controls the physical aspects of these polymers. And then certainly cross-linking as well. Those are all components of polymers that can make one different from another. All right, and so we have structures of various polymers, and so you will again have the, I'm not sure I did this last year, but I'm going to keep doing it. You will have the memorization question at the beginning of the test, and that's going to have the 6 that you're used to, plus, you should still memorize the big 6, plus that last one. As far as the rest of these are concerned, you don't certainly have to memorize them, but you should be able to recognize them. All right, which there's only a few that are difficult to recognize. The rest of them are pretty straightforward as far as that goes. So where these guys may as one, and then acrylamide, acrylic acid, polyvinyl acetate, those are the ones you kind of have to be able to tell apart from each other. Plus that guy, polycarbonate, not too hard to memorize, but that's the number 7, all right, beyond the big 6. All right. And then the nylon-based structures, I'm not going to say which nylon is it, is nylon 6 or nylon 7, unless that's part of the question. PET you know, and polyurethane you should be able to recognize. Right? So these are structures that have characteristic bonds within them, so you should have a pretty good idea of what a polyurethane structure looks like. Please don't memorize it, but just know what it looks like, okay? Any questions about that? Okay. All right, so getting into some of the details. So we have free radical polymerization. One of the most common and useful reactions for making polymers. In fact, there were a lot of polymers at the beginning that were made using condensation reactions, and they said, well, this is terrible, and they figured out how to make it using addition reactions because it's much cleaner. There's no side products. All right, so there's plenty of examples of that in history where they said, condensation is crazy difficult. So that everything, when they can, uses free radical polymerization techniques, and that includes the ring opening polymerization, which it's very similar, and that's a nice clean reaction. It doesn't leave you any byproducts you have to get rid of. And we should, at this point, knowing what we know about how polymerization takes place, realize why that's important in terms of controlling polymerization. Okay, so one of the most common and useful reactions for making polymers from vinylic monomers. And of course, these have these double bonds, which are key to the process of the initiation of the radical, which then leads to polymerization of itself with its neighbors. All right, that's all something that should be pretty clear. And we have key aspects of this that kick the process off. These initiators, AIBN or BPO. Okay. Again, you don't need to memorize those structures, but you need to know how they work. All right, what do they do? How do they kick the process off? Why are they so darn important? And then propagation is growth of the polymer chain by the successive addition of monomers to that active center, that end of the chain. And we have a couple of things that are important to us. We have coupling termination, which is typically what we like to get to high molecular weight, and disproportionation termination, which is not so desirable. All right, as you'll see, and as we've seen before, that has molecular weight differences, those two different modes of termination. So typically we like higher molecular weights, so we like the first one better. Any questions about that? Bless you. All right, and so we have initiation leading to the formation of these free radicals. Free radicals find other monomers, which consist of those vinylic carbon-carbon double bonds. All right, attacks and breaks them open, and the whole thing starts to propagate out into the available space. So you have the termination reactions, coupling, in which two ideally long chain ends find each other. And so in three-dimensional space, you can start to recognize the fact that, as these get longer and longer, they consume all the monomer around them, and so these two guys finding each other may not be so easy. All right, so it's just, a 1.5 angstrom moiety trying to find another 1.5 angstrom moiety, and so in three-dimensional space, that may not be so simple. But the good news is they're highly reactive, so eventually they come into contact with each other, and then bang, they give you that nice long polymer chain. On the other hand, we can have things that are not so desirable, the disproportionation reactions, which end up reacting with themselves or shutting down, and they give us chain lengths that aren't quite so long. They also they're also broader. If you recall, the DPI, which you guys know now, is larger for disproportionation than it is for coupling. Okay. Initiation is relatively slow but continuous. Molar mass builds up very fast. We talked about how it's a matter of seconds for some of these. And seconds is considered a long time in these polymerization reactions. All right, so the process of making the polymer, when you control your conditions correctly, is actually pretty fast. Reactant in, polymer out, just keeps going all day long. All right, any questions about that so far? All right, and so we introduced the concept of what dienes are. And these diene classes have these double bonds, and there are different subcategories: polybutadiene, polyisoprene, and polychloroprene. And these have different groups within them, which give rise to different types of properties. You should have some idea what they're good for. Generally low TG materials that are used as rubbers, when it has the cis structure at least. When it has a trans structure, you guys should know that it has completely different properties. Right? So cis and trans aren't small abstractions that people in organic chemistry have to worry about. It turns out that you can completely change the physical characteristics of these polymers based on whether it's cis or trans. Big differences in behavior. Natural rubber source is 90% of that cis structure. So rubber plants in South America. Okay, and then we get, especially in this portion of the class, into copolymers. And this is one of the classic reasons why we were about copolymers, or why we think that they're so useful. Polyacrylocobutadiene costyrene, ABS. And it's the archetypal example of a useful and very flexible copolymer structure, which has these three components to it, which are represented by the different ratios MP and N. And so we can change MP and N all day and all night, depending on how we feed monomers in the system and what the reaction quantities are. We can get a ABS that utilizes all the bonding we're looking for, but because of the different amounts of P versus M versus N, will give us very different properties. Okay, so we can make a flexible ABS, we can make a rigid ABS, all by controlling those different numbers, those different fractions. And so this is a key aspect of the tailorability of copolymers. It can make them so darn useful, even in a structure that looks relatively complex, but surprisingly has a lot of utility. And so what we're looking at in this context, and again, this should be part of your understanding of copolymers, this is nitrile groups. So we think about hydrogen bonding, holding the chains together. We have the rubbery polybutadiene, which even in the presence of this strong hydrogen bonding gives us rubbery behavior, all in the same matrix. And PET is very similar, right? It has aspects of it that make it stiff, and it has aspects of it that make it rubbery. And so we get to this best of all possible worlds, and again, we can vary those three inputs and tweak ABS properties very tightly. And so the rest of this should be pretty straightforward, and even though we don't make landline phones anymore, at least not very many, it has utility in a lot of other areas. All right, any questions about that? So step growth polymerization, and so we think about the different aspects of monomers A and B reacting with each other to give us D, and then we can have some limited initial polymerization of A with A, and then B with B, combine those together, and this is where we start to get these copolymer type structures, and then we can combine them and get alternating copolymer-like structures, all with these types of step growths. So you can take the step growth process and tweak it to change the output, and that's kind of the precursor to a lot of the different naming aspects of copolymers. All right, and so this is just showing you the kind of feeds that go into making polyesters, which you should know what those are, polyamides, you should know what those are, and polyurethanes, you should know what they look like, I guess I should say. And so this shouldn't be that difficult. And as I said before, I give you these think of them as abbreviations, but in your mind's eye, the three-dimensional structure of the carbonyl, the hydroxyl, the amide groups, all those things should be something that you see when you look at these structures. And if that's not the case, you definitely want to try to brush up on that. So these are different things that you should know about these types of different inputs. And then the Carruthers equations, very important equations. In most cases, what I'm going to do is I would just give you numbers and say, give me some information about how this works in the end. So you whip out your calculator and perform some of these calculations. And that's pretty much the extent of it. Shouldn't be that hard to fathom. And then, of course, part of what comes out of things such as this value for issues associated with purity of inputs are an understanding of why we need certain types of purity, and then we want large extensive reactions, And this issue of the functional groups needs to have an R of exactly 1, ideally. Whoops. So now what did you do? Okay. And this is showing you polyurethane, and so this is kind of goes beyond what you know about polyurethane based on the chemistry, based on the reactions. You're putting these nitrogens and carbonyls together in the same polymer. What does that mean in the actual structure, and what does it mean in terms of the biomedical implants that go into people? They consist of areas in which hard segments gather together and hydrogen bond with each other, and then soft segments which don't hydrogen bond to each other. And so again, it's all part of this game we play between rigidity and mechanical properties and softness and mechanical properties, and how we control that. So we can do that at a very local level, or here, very importantly, we do it at a somewhat less local level. It's more like a microstructure that we would think of as microstructure in the context of polyurethanes. And all the associated aspects of glass transition and the kinds of things you'd expect for these different types of areas, hard segments versus soft segments, et cetera, et cetera. Any questions about that? All right. And then in terms of a couple of additional things, ring opening polymerization, and as I mentioned at the beginning, it's kind of like addition polymerization. It's a very clean process, but it involves the hard part about this is really making these rings. And so once you got that chemistry work out, how do you make a ring? And these rings are typically pretty highly strained, all right, and they're just itching to break open and react with something. So when the right conditions, the right purities, temperature, catalyst, etc., they break open and react with each other, and they make PLGA or PLA or PGA, all these biomedical polymers that if you go to the doctor, you get a suture containing these things. All right, so that's all part of that chemistry, which is obviously a very important chemistry. It's not truly additive, all right, but it has the same benefits, and it doesn't have side products. Okay, and then thermosets. So beyond the abstraction of these complex cross-linked structures that we think about as far as the spaghetti model of thermosets and these 3D polymerized structures, we think about what do we need in terms of the chemistry in order to make a thermoset. And this is a couple of examples of, first off, the linear stuff we've been talking about, but now we extend that into groups that have 3 areas which they can bond. So some other linear component can react with any one of those sites and give you reactions that go off in 3 directions rather than just a straight line. So it's no longer a linear chemistry, it's a 3-dimensional chemistry. And then when you make those types of structures, hopefully at this point you have a real appreciation for why those structures have such a strong effect on particularly mechanical properties. Okay. And then copolymers, homopolymers, you know the difference. And then we get into the naming sequences. And so we've went through this in class, but polyco-AB, poly-A stat B, ran-B, alter-B, and then these alternating, one of your homework problems involves that type of question, so you should be able to name these things based on what you see in a problem statement. It's not that complicated, but you do need to be able to recognize things. And then these periodic copolymers as well, and then block copolymers, which are probably more important than some of the other ones I mentioned, but these are certainly all used in different places. And the different representations, poly-A, block, poly-B, or poly-AB, which is easy to write. And then some examples here, what you need to be able to name them based on what you see in those structures. All right, based on what you know these acronyms are good for. Graph copolymers, which typically consist of something highly recognizable in the main chain A. So it could be like a polyethylene or a polypropylene. And then we turn around and we graph something interesting on the sides to give it additional properties that polymer wouldn't normally have. And so these graph copolymers do have very specific uses.
What's the main difference between this and like just the alternating polymer with the side groups? Like you have to have significant, to like show like significant chains coming off of the side?
Yeah, so the chains have to be of a certain length. All right, they're typically not just short side groups, no. Any other questions? And then this one example of high-impact polystyrene is one such example, which allows you to really localize the softening groups in that polystyrene and get probably better defined properties than if you just mix things together, which you can still do, but this gives you better control. And then star block copolymers, what those mean exactly. So this would be a place where there's a ton of examples in the literature. I pull out an abstract and they say, here we made this star copolymer and here's why. All right, so you should have an idea of what those structures are and what that means in terms of properties. And then the net-like structures, differences between polymer A and polymer B, and how you name the result based on how they're linked together or not linked together in some cases. This shows you linkages between the different polymer A and B. But then we get to these network structures which may exist in space together but are not chemically bonded to each other. Okay, so we have one network that is polymerized first and the other network is polymerized second, and there's no chemical bonding between them whatsoever. Plenty of secondary bonding, of course, but the covalent bonds are just between A and B, not between B and A. All right, so these give you interesting properties. And then variations on this theme where you have a cross-linked version of polymer A and a linear version of polymer B gives you these semi-interpenetrating networks, which are probably more interesting and more useful than the different nets themselves. Semi-interpenetrating is still a hot topic. Any questions about that? All right, so this table, hopefully you can look at this table and in your mind's eye know exactly what every one of these things is. Any questions about that? Okay.
Certain like shapes like polystyrene, like not the styrene, like polyamides,
You mean am I going to give you something that you're not familiar with, or what are you asking? If I give you an example, it's going to be like polyethylene, polypropylene. It's going to be big 6 polymers. Okay, you don't freak out too much about that. Okay. Any other questions?
So we do need to memorize.
All right, and then in terms of an overview of the lectures that came after that, we have configuration, which most of us know now pretty thoroughly. These issues involving interconversion and the fact that it is only capable in some cases by breaking the chemical bonds, which of course I have to tell you that. Never assume that. All right, just assume that we're talking about secondary bonds for the most part unless I give you information that suggests otherwise. And then geometric, substitutional, and stereochemistry in these different polymers. What does that mean? We already talked about cis and trans and why that's important, and we also know that's important here as well. All right, cis on the same side, trans on the opposite sides. You need to, as you can see here, kind of recognize that when you look at a structure, because that could be part of the naming sequence for a given polymer or copolymer. All right, so keep that in mind. Very different mechanical effects based on these different types of cis and trans stereochemistries. And then tacticity, which I believe everyone knows pretty darn well. You should be able to recognize these. And naming can be significant as well. So make sure you understand that also. All right, and this for the most part we understand, I believe, and we should know that isotactic and syndiotactic, if I have an isotactic polypropylene and a syndiotactic polypropylene, they can both crystallize. They're not going to crystallize the exact same amount. All right, there will be differences. Just because one can crystallize and the other one can doesn't mean they give you the exact same percent of crystallinity. On the other hand, atactic structures should be completely amorphous, and for polystyrene that's typically always true because we don't want it to crystallize. It's already rigid enough without being crystalline. And also, as part of the fact that they have different crystallinities, they also have different properties. And then we also have the expected effects of thinking about crystalline structures in polymers as being like little rocks, all right? Little rocks with strings going in and out of them, all right? You should be thinking of it that way, even though, yeah, we know it's an organic structure and know it's not going to bear load, but the approximation is still useful in terms of thinking about their effects on properties. Any questions about that? All right, and so it's chain structure 2, as I say here. We have conformation, which refers to the order of atoms or groups in space that arises from the rotation of molecules around the single bond. Okay, so that's conformation, and we try to characterize this in different ways using this polymer chain end-to-end distance, which is not the same thing as the end-to-end stretched out distance, okay? Well, actually, I guess it is in the extreme case, but in most cases, when we talk about polymer chain end-to-end distance, it's something we're characterizing in real polymer systems, and it involves that distance, not this distance, all right? So we worry about this one and not so much the other one, which is really darn hard to measure, first off, but we can measure the other one. And so we talk about the root mean square statistical average, which is r squared to the 1. And as you'll see in the homework that I'm about to send out, we can calculate these different components based on different models, how we regard polymer chains in space, how we can try to model the structure and the limits on the structure, whether it interacts with other chains or not, whether it's got free rotation or not. All these things you should be able to, especially after I send you the homework, be able to plug and chug your way through them. All right, so the problems I'm going to send out, just look at those and say, well, he can just change this number of 10% over here and that number of 5% over there, and I still need to be able to work through the numbers. Okay, so make sure you're familiar with that. And if you haven't used a calculator in a while, I don't know if that's true or not, it's been a while since physics, right? It would behoove you to gain familiarity with the calculator again. And so we have some examples here in terms of these different components and this C infinity, the characteristic value, concentration. You need to know how to use that. And then, of course, these, again, once you work through the homework, this should be all pretty straightforward. All right, so. And then molecular weight. So yeah, you really need to know the difference between n sub n and n sub w. Please don't think of them as the same. They are not. All right. And also that m sub w, m sub w is always greater than m sub n. And we use that ratio to come up with the polydispersity. And polydispersity is important to us, depending on the applications. But we know that a polydispersity of 1 is meaning that all the chains are the exact same length, which is rare, but there's typically an association between the quality of a plastic and the PDI. The lower the PDI, the higher the quality of the plastic. May not make that big difference in terms of the application, but we still look at it that way, just because if you have that low molecular weight stuff, which as I mentioned before, can be done deliberately to give you different mechanical properties. And that's where control starts to creep into it. Any questions about that? And then these relatively straightforward.
Actually, I have
oh yeah.
a question. Will you ask anything about like MZ or the other? What was the other
No,
one?
I will not ask about MZ.
Because that's like
or MV. Yeah, no, definitely not going to ask about that because I've been doing this for a very long time and I've never looked up a polymer and seen its MZ listed in the catalog. So if I've never encountered it in the catalog, you guys aren't going to see it in the catalog either. So I don't feel you need to be responsible for that. Any other questions? And so we have these expressions for m sub n based on what type of termination we have, whether it's coupling or disproportionation. And am I going to ask you to memorize these equations? No. Okay, good. All right, so we're all on the same page. So I'll give you the equation and say, here, crank out these numbers based on this type of termination.
Plug in the terms and know what the terms mean.
Yeah, exactly. Okay, and you were given an example in the notes and so forth, so you should look at that and get a handle on what that looks like. And then we have these issues associated with the molecular weight and the type of polymerization, in this case step growth polymerization. And an example given here involving compute for this particular polymer when a given extended reaction is provided, and crank out the m sub n and m sub w and PDI along with that. Pretty straightforward stuff once you have the numbers in front of you. Okay, and then more recently, we talked about how polymer molecular weight affects dissolution rate, and you should understand the why of that pretty thoroughly at this point. That harks back to the previous discussion about dissolution to make crystallinity more obvious, but in this context, we're thinking about issues associated with whether a plastic is useful or not in a given environment. How does temperature affect that? And this, hopefully, everyone has fully believed the concept of chain motion and temperature. It's not just energy, it's motion. All right. When I talk about temperature, the thing you should think about is motion. Don't tell me about polymer energy. Whatever, that's a really amorphous thing, polymer energy. But motion, yeah, that's very significant in terms of properties and behavior for these different plastics. And entropy is kind of a part of that, but don't over rely on entropy as the answer for everything either, which can happen sometimes. Let's see, amorphous dissolution temperature, glass transition, above and below TG or TM, all those things should be obviously important, involving the chain energy and how that influences the inflow of solvent and the outflow of polymer from a given block. Okay, so hopefully that makes sense. Let's see. And then, this can a cross-link polymer dissolve in the solvent? No. All right. So unless I tell you otherwise, the answer is going to be no. All right. So yeah, you can put it in concentrated hydrosulfuric acid, of course, and anything will dissolve. But under normal circumstances, the answer is no. Okay. And then the whole like dissolves like thing is simple but effective, and you should be able to get an idea of what the answers are to this question. All right, just by looking at this, you should know the answers to that question. Like dissolves like is important to us. Polar polymers, polar solvents, nonpolar polymers, nonpolar solvents. General rule, however, of course, there are exceptions. Unfortunately, I wish that it was cleaner than that, but you can make general predictions about like dissolves like, and most of the time they're observed, they're not. And then the issue related to that, solubility parameter, again, an attempt to try to codify and quantify the behavior of polymers when they're exposed to given solvents. And so we come up with this term delta, which we can either look up or calculate and try to predict whether or not they will dissolve in specific solvents. All right, so we're looking at delta matching, basically, between solvent and polymer, and using that to predict whether something will dissolve. And then homework problem you'll see shortly involves calculating that based on this table 3.3. And so as you work through those problems, make sure you get a handle on using table 3.3. I went through this in the lecture, so hopefully nobody's confused by how they try to type things into a table as opposed to draw them. Okay. Any questions about this table? So I'll give you the table. Don't memorize the table, please. All right, and then ask you to go through and crank out these numbers. Okay. And so we can think about this in terms of working with a given polymer structure, counting the number of groups, figuring the contributions to delta based on the table, and then summarizing this in the form of an overall delta that can be used to look at that table and say, oh yeah, this is going to dissolve, or this won't dissolve. All right. All right, so what's going to be on this? Let's see. Name polymers, short answers, true, false. I don't know if it's going to be 2. It's going to be at least 2. Probably more like 3. Depends. All right, so keep that in mind. But you will need your calculator All right, you didn't for the first 2 exams, but you certainly will for this one. All right. Any questions on that? Just on an overview, just capture everything that you really need to know. Yes?
So there's also going to be the big 6 at the beginning of it too?
Yeah, so I'm going to go ahead and do that this year. We'll have the big 6 at the beginning plus the 7th one.
Mm-hmm.
Okay? You may not see that in the old exams, but it will be on this exam. All right, so I'll put the homework on Carmen after I have a 4 o'clock meeting, and then after that, hopefully I'll be able to get around to putting it on Carmen. And then the old test as well. And the homework will be due on Monday, and the test is on Wednesday. Any other questions, concerns? Yeah? What?
Is the homework posted?
Right now, no. When I get back to my office and have my meeting. Yes?
Do you want us to hand in a physical copy of the homework or fully submit it for Carmen?
Unless, I think you kind of have to be a glutton for punishment to do it online. I would tend to write it out by hand. It's all these calculations. You can do it either way, as long as you get the work back to me. I guess you could write it out and scan it and send it to me, but...
What's in the homework? Like just problems like this?
Yeah, problems like that, right. Is that all clear? So...
Okay, so we can either submit it to
You can if you want to. If I were you, I'd write it out on a piece of paper and yeah. You could do a mixture. No, please don't mix the
just,
two.
write it on paper and we have to print out the actual assignment.
So I will send out the homework, and it's going to be the problems next to each other. And if you want to type out answers, you can. If you want to handwrite answers,
What
you
I'm saying
can.
is like, can I just write like on the paper 1 answer?
Yeah.
I don't
Sure.
have to like
Oh, heck
print out
no.
the
You don't have to
question or
restate the
copy
question. No.
Okay, so
Yeah,
I don't
don't-
need to turn the questions to, just the answers.
Exactly. Yeah.
What you've seen and make some type of like outline. Yeah, some type of outline, and like even if you